In this video, I'm going to introduce you to OpenCV. OpenCV is a programming library. It contains many different computer vision algorithms, and it's open source, which means that you can look at the source code and change anything that you want. By using computer vision, you can teach computers to see and understand the world, or at least an interesting part of it. There are many current and future applications for computer vision. Because of that, different libraries or tools have appeared over the years to help developers. Why should you use OpenCV instead of other libraries? First of all, it's distributed under a BSD license, which means that you can use it for personal or commercial projects for free. It can be used with Linux, Windows, or Mac, and you can code your application using either C, C++, Python, or Java. And it's popular. It means that new features will be added, bugs will get fixed, and you have a community for asking questions. Also, you can develop mobile applications for Android, iOS, and Windows Phone 7. OpenCV functionality is separated into modules covering different aspects of computer vision. Some of the modules that you will learn in this course are image processing, object detection, panorama stitching, computational photography, calibration, 3D, and others. Using those modules, you will be able to create computer vision applications. When you see a new version of OpenCV, you can instantly have an idea of what has changed. The first number represents big changes in the library, like the change from C to C++ as the main interface when it changed from version 1 to version 2. When the second number increases, you can expect new features. And if the third number changes, there were small changes or bug fixes of the previous version. Now you have a general idea of what OpenCV can offer. You can go to these websites for more information. In this video, I'm going to show you how to install OpenCV in Linux. So for that, I'm going to use my guide, which is in samtab.com. And when you go there, you can just go to image processing, and then you can just go to installing OpenCV 2.4.1 in Ubuntu 12.04. And after you do that, you will have a step-by-step guide that you can use for installing OpenCV in Linux. So the first thing that you need to do is to get your system up to date, which you can do by just updating and upgrading your system. I already did that, so I'm not going to do that again, but you should do that. Then you just need to install all these libraries. There's many libraries, but you can just copy and paste them here. And you just put your password there, and that's it. So you can see I have everything installed already. It will take some minutes for you, but I already have everything here. Now you need to get the OpenCV code. So basically you can just go to your, these instructions are just go to your home directory and get that and extract that into OpenCV 2.4.1. So I already did that, and here's what you should have. So some files there. I already have that. So after that, you need to create this build directory. Go to that directory and say to CMake what you want to build. So just go to build and paste that. You can just go and copy and paste every single line, but I already did a couple of them, so I'm just saving some minutes. So as you can see here, I want the examples, and the documentation will be built and other things as well. For example, I'm using the TBB and Video for Linux, for example, FFmpeg, which is basically working with videos, some libraries for working with images, and this is important, Qt 4, which is new graphic user interface, which is very cool. You should use that instead of the normal graphic user interface. It's much better, the Qt one. Okay, so now it's finished, and as you can see here, we have something similar to the image here. So now all that you need to do is just type make, but it takes a long time, so I already did that, so I'm not going to waste, it takes like 20 minutes, 30 minutes, so it depends on your system, so I'm not going to do that again. And then when it's finished, you should install it with this command here. And after that, it should be installed, but you need to do a couple of things. For configuring OpenCV, for example, this, you just copy and paste that. And in that file, you just need to add this line, user local lib or library. So I already did that, and you add that, then you just click save and close this file. Then what you need to do is run this line. Then you need to edit this other file. So you need to add these two lines into this file just at the end. So you open this file, just go to the end, and then in the end just add these two lines, and that's it. You just add the two lines, save, and close the file, as you can see here. So now, as you can see here, you need to close the console and open a new one, restart the computer, or log out and then log in again. So in this case, we're going to exit, and we're going to open a new console again. So now we should have OpenCV installed, so you can see how cute interface is. See, so if you go to the samples, and I already built them, so you can just copy and paste that, but I already built them, so you just need to follow the instructions line by line and you should get the same thing. But as you can see here, it's very cool. You can just browse and see the image and move the image around. You can click these buttons and you can save the image if you want, or you can move the image. But the cool thing is that if you zoom in a lot, then you will start looking at the value of the image, of every single pixel. You will see the red, green, and blue, the values, or even the intensity value if it is a grayscale image. So that's very useful in general for working with OpenCV. So that's a great graphical user interface. So that's it. Now you can just run all these other samples, and even with Python, for example, you can just run that, and in this case you will see how it will start changing from something random to some specific features. So that's a cool example. You can see it for yourself. And that's it. Now you have OpenCV installed in Linux. In this video, I'm going to show you how to install OpenCV in Windows. First step that you need to do is to download a couple of programs. First program that you need to download is CMake. You can download it from cmake.org, and you can just download and install it using the default options. That's fine. And also you need to download the Visual C++ 2010 Express edition. If you have the professional version, that's fine. You only need the Express version, which is free. So if you have anything better than that, that's okay. It works with even with the Express version, so that's fine. So once you have those two programs installed, then you can just go to download the OpenCV files, which you can get them from the SourceForge page. So basically just go to SourceForge and you download the latest file for Windows, which in this case is OpenCV 2.4.1, and you can just download that. After you do that, you have this file, which is basically, if you double click on it, it will ask where to extract it. You can extract it anywhere that you like. For example, in this case, I extracted it in my desktop. It doesn't matter. So I just extracted it before. So it's here. You will end up with this structure. So once you have that, the only thing that is important is that you need to know where you extracted the content. So in this case, it's this. So basically you need this path. So when you download and extract OpenCV, you only need to go to CMake, OpenCMake. When you open CMake, you need to put here the source code, which is just exactly the same place that you just extracted your code. Desktop OpenCV in my case, it can be something different in your case, but if you extract it in your desktop, it should be something similar. And then you need to give the program where to build the binaries. In my case, I use C OpenCV, which is a good choice in general because I'm not using any blank space or any strange character. So C OpenCV is pretty much a good choice. So you can use that. So if you do this the first time, you will not see this in red. You will see like nothing here. So for example, if I change this, so you will see something like this, but the only thing that you need to do is just to click on configure and it will read this folder and it will create these options here. So the only thing that you need to do is put here where's your code, here's where you want to create your build code, and click on configure and it will ask you to create the new folder. You can just click on yes and you will be in the same place that I am right now. So after that, you can just select any option that you want, or you can just accept the defaults and click on configure again. So if you click on configure, it will start to check your environment and create everything that you need to start building your software. Now it's done. So in this case, I'm using Visual Studio 2010. And the only thing left here to do is to just click on generate. If you click on generate, it will create on this folder, C OpenCV, the project that you need to build to create the OpenCV library project. So if you click to generate, as you can see here, it will create everything that you need to open a solution here. Okay, so I already had that open, that's why it appeared. So now it's done, and what it did is it created this folder, C OpenCV. If you go there, you only need to go to opencv.sln, which is the solution, and if you double click that, you will open the OpenCV solution. The thing that you need to do is to build it in these two different configurations, in debug and also as a release. Once it's finished loading, you need to go to, okay, so these are, it seems that there are problems, but you can just treat them as warnings. Just because I'm using the Express version, it's okay to ignore these problems. You can just think of them as warnings because I'm using the Express version. It's not a problem, it's not an error, it's just a warning because I'm using the Express version. So this is okay. In debug, you just need to go to debug and build solution, or just press F7 and it will take some minutes. I already did this, so I'm not going to do this here. But then when it's finished, when it says that everything is done here, you need to change it to release here. It will load all the different things that it needs to build a release version. And when it's finished loading everything, you only need to go to do the same thing. Just go to debug and build solution, or just press F7 for release. So what you're doing there is just building the libraries for the release and debug versions. So when you're finished with that, so remember, right? You just go to debug and release and click on debug build solution. You have to do that twice, one for release and one for debug. When you're finished with that, here inside the binaries, you will have a debug and release folder. Inside debug, you will have all the debug libraries, which ends with a D. And you also have all the relays libraries, which doesn't have a D. So you need to add those two into your path. So how do you add that? You just go to control panel and you search for path and just click on edit the system environment files or variables. And here you can just click on environment variables. Here in system variables, you need to go to path. You can just click P and you have P, edit, and here you just need to put that. Wherever you have in your path, I choose C OpenCV, and wherever you have there, you need to add binaries and debug, and then also you need to add OpenCV binaries release. So you add that to the path, and that's everything that you need to have OpenCV installed in your system in Windows. So now, if you follow these instructions, you should have your OpenCV installation ready to work in Windows. In this video, I'm going to show you the different OpenCV interfaces. The main interfaces of OpenCV that currently has is C, C++, Python, and Java. The C interface was the first interface to OpenCV. OpenCV 1 used this interface, and it has been around for many years. That means that there are many examples or tutorials that use this interface, but it's mostly not recommended for use today because we have different interfaces now. So the only way that you will need to use this interface is to make old code run. For example, any example that you find on the internet or any old code that you have running around. The C++ interface is the main new interface of OpenCV, and from OpenCV 2 onwards, this is the suggested interface. So if you're building a new project or you have a new code, you should use this interface. It's the most detailed interface that OpenCV has. So every single function that is available in OpenCV should be available from this interface. This is the recommended interface for starting a new project. Also, there's an alternative to the C or C++ interface, which is Python. It's almost as complete as the C++ interface, but it has some specific details that are not available. But most of the functionality is there. So if you normally use Python to work, you can still use it, and it's a pretty much complete interface. But the most complete interface is still C++. But if you really prefer Python, then it's okay. It's an almost complete interface. Also, there's a Java interface, which is not as complete as the C++ one. And it's basically for running OpenCV on mobile platforms. That is the main objective of this interface, at least for now. So it's not as complete, so you shouldn't use this interface for normal desktop applications. But if you want to run OpenCV on mobile platforms, then this should be a good interface. That's it. So now you know all the existing interfaces and which one you should use depending on your specific project. In this video, I'm going to show you how to use the C OpenCV interface. So you will know how to load an image and access the pixels and write them to have something like this. First, I'm going to show you the code. So you need to include these two files. cv.h is basically most of the functionality of OpenCV, and this other file is needed for the windows that you just saw. So anything regarding to input output of high level. Okay, so these are my functions that I defined, and this is the images that you notice that I'm using IPL images. That's specifically for the C version, the C interface of OpenCV. It uses IPL images. And then we can see the main part of the code is here. First thing that I do is to create two windows. You can access the windows later by their name, so image and process image. Then I proceed to load the image. Here, CV load image. You just need to put here the path of the file that you're using. In this case, I'm using this file, so that's the name there. And then if there's any problem, it will exit. Then I will process the images and then just display the images. This function here is used for not immediately exiting the program, just waiting for a key from the keyboard. So this is just for that. The moment a user presses a key in the keyboard, the program continues. Then this is another important part. You have to release the used memory in the C interface. Every time that you create or allocate memory in an image, you have to release it later when you stop using it. So for every image that you created, you have to call CV release image. And in this case, I'm using two of them. Okay, and then you can call this function to destroy the windows that you have. Display graphics is very easy. You just call CV show image with the name of the window and the image that you want to show in that window. And the processing is a little bit more complicated, but it's not as hard. We can see I have here the basic IPL pixel is an unsigned char with three colors, red, green, and blue. And first I start this by just cloning, getting a copy of the image in the processed image. And then beginning vertically and then horizontally, I'm accessing all the pixels from 0 to height and from 0 to width. And first I get the value of that specific color of the pixel. As you can see here, it's a pointer to an unsigned chart. You get to the data and then you go from one place to the other, just following these rules. So the only thing that you need to know here is that you advance one step vertically here in each step, and then one step horizontally. But in this case, you need to multiply that step for the number of channels, in this case 3. And then you just offset it by 0, 1, or 2. So that means the order of the colors inside the image. In OpenCV IPL, you have BGR order. So the first pixel, color pixel that you get is the blue, the second one a green, and the third one a red. So in this case, I'm just getting that, and the unsigned chars go from 0 to 255. So what I'm doing here is just inverting that, so getting the difference. And in the same place, I'm just putting that difference into that specific place. And I do the same for the other values, and that's it. That's everything that you need to know for that. And then for compiling it, you can just go and do this, and what it's doing there, you can see that I have a pkg config. For example, you can call the libraries of OpenCV, and you can see it there, or you can have the flags of OpenCV. So in this case, you can use this method for compiling, because mostly if you want to use the C interface, mostly you want to deal with all code or interfacing it with other software in strange ways maybe. So I prefer using this method for compiling the C interface. Just easier than CMake. In this case, if you use the C++ interface, it would be better to use the CMake. So as you can see here, with pkg-config, I can get the specific includes that I want. I have to include that in the compile line using this symbol here and here to get the output of that command. That's the only thing that you need to do. You can just include more directories here and call it wherever you want. OpenCV and pkg-config takes care of everything regarding to the include libraries and stuff like that. So you can just run it, and that's it. Now you can use the C interface for old code or some examples that you find in the web. In this video, I'm going to show you how to use the C++ interface to OpenCV. We're going to open an image, access to the pixels, and write the pixels in a different way to inverse the image, as you can see here. So the first step is to show you the code, and here it is. The first thing that you have to do is to include one file, this opencv.hpp, and that's everything included there. Then all the functionality of the C++ interface is inside the CV namespace, so you can start using it from here. I defined two functions for this example, one for processing the images and another one for displaying the images. And here you can see the two images that I defined, image and process image, but the important thing is that I'm using mat from Matrix, and this is the main difference from the C interface, which used IPL images. The C++ interface uses Matrix for storing images. Okay, so here's the main code. I create two windows with names, image and processed image. I load the image with this function, IMRead, and you only need to give it the path of the image here, as you can see. So if the image is empty for any reason, the program will exit. Okay, so first I process the images and then I display the images. And this line is just for waiting for the user to press any key on the keyboard. And that's it. When the program is finished, you don't need to release any memory in the C++ interface. Everything is done automatically using the destructors of the objects that you create. So you don't need to manually release memory. As in the C interface, you need to release memory manually, but in the C++ interface, you don't need to do that. So now for displaying graphics, it's very easy. Just call imShow with the name of the window and the specific image that you want to show in that window. And in the process image, we're going to use vector of pixel. Actually is free unsigned chars vector. So you can use that in the C++ interface, and also the three colors, as you can see here. So the first step is to clone the image. So if you have one image, you can just call the method clone, and you will have a process image. If you were using this image before, it doesn't matter. Everything will be removed. All the memory that you were using will be cleaned. And if you don't have anything allocated here, everything will be done for you. That's a great thing to know for the C++ interface. It's very easy to use. So now we're going to go for every pixel of the image. So we go from 0 to the total number of rows and from 0 to number total of columns of the image. and we're going to get the pixel. So basically pixel, you can get it as just saying give me the, in this image at yx, it will give you the pixel at x, y. And after that you get the pixel, you can access it from BGR, which is the order of the colors in OpenCV. The first one is blue, the second one green, the third one red. And then you can do whatever you want with that pixel. For example, in this case, I'm complementing the color. Unsigned chars go from 0 to 255, so I'm just doing the conversion there. And after the pixel is ready, I just write it into the process image again. So in the same position that I was reading it, I can actually put the pixel in there. And for compiling it, I'm going to use CMake. First, I'm going to show you the CMake code, which is very small. So you need to create a file called cmakelists.txt, and you need to add these lines. They're really simple. You can just copy and paste them. So you need a minimum version of CMake, and you can have a name for the project, and you have to require OpenCV, and you need to add the, this is the file name, and this is the executable name, and also for the libraries and the project name. So when you have that, the only thing that you need to do is to call CMake and the directory, in this case the same directory, and it will create a make file for you. So it created everything needed, and you only need to do is put make there, and it will create your executable there, CPP interface. And that's it. Now you can use the C++ interface of OpenCV using CMake. In this video, I'm going to show you the Python interface of OpenCV. We're going to open an image and access to the pixels of the image and change the values of the pixels so we have inverted color image, as you can see here. So the first step is to show you the code. The code is here. The first line, it's importing CV2. That's the Python interface that we are going to use. Then we define two named windows, image and processed image. And then we read from the file. So we open an image with IM_read, and we just give the program the name of the image. In this case, it's this one. Okay, so first I'm going to copy the image that I just loaded. I'm going to copy it to the process image, and then I'm going to access to the pixels of that image. So in the process image, I get the height and width, also a number of colors, and then I'm going to get all the pixels vertically and then horizontally from the process image. So you can access the pixels with this method item. So if you want the XY, you just have to access it by YX, and then this offset. This offset means blue in this case. OpenCV has BGR order. So the first one is blue, second green, the third one is red. And you can get the value of those pixels. Those pixels have 8 bits. Those colors have 8 bits, so they go from 0 to 255. So the next thing that I'm going to do is to set, as you can see here, the function item set in the same position with 255 minus the specific color that I have. So by doing that, I'm inverting the colors. So you can see that it's very easy to access the pixels here, to read them, and then to write the pixels here with item set. So you can read with item and write with item set. And then we're ready to show the images with just IM_show. The name, you just need to put the name of the window and the name of the image that you want to use. Same here. Then you need to call this function to wait for the user to press a key. on the keyboard, and then you just destroy all windows. That's it. So you can run it by calling Python and then the file main .py, and you can see it here. When I press a button, it closes. Or you can add the executable state to the file, and then you can just run it, and you can even have an argument there. And that's it. Now you know how to use the Python interface to OpenCV, read and write pixels to the screen, and if you want, you can save this image here. In this video, I'm going to show you how to draw into an image, as you can see here. So I'm going to show you the code, and here it is. The first part is very standard. You include the OpenCV files. I define my functions. I read an image, and I define a window and process image, display graphics, and then I wait for a key. And here's the important part where I process the image. Okay, so first I define some colors, blue, green, and white. As you can see, it's in the BGR format, as OpenCV uses that. For example, here the largest numbers is the first one, which is B, so it's blue, then green, and white. Also a thickness and a line type. This line type is anti-aliasing, so it looks better than the normal, which is 8, the other type. Also, I define the position of two eyes and the radius of each eye. Also, I define the center of the face. So these are the eyes and this is the radius. I also define the face center, which is around here. I also define the size of the face, which represents the rectangle that encompasses this ellipse, and the angle. As you can see here, there's an angle in the face. Also, I define the text. This text here is just a string, and some properties of the text, like the scale, thickness, font, or the font start is the first point where the text begins, so it's around here. So then what we do is to get the text size, to put the rectangle around the text. So you get the text size with the same properties that you're going to use to write the text. Then I get these 2 points, point 1 and 2. Point 1 will be around here and point 2 will be around here. And I just calculate it with the size of the text, the height and width. And I also add a border. Up to here, in this point, P1 will be around here and P2 will be around here. But that's too close, so I want to add some border. And that's what I just do here. So I subtract to get up to here, and then I add the border to P2 to become up to here. And also I calculate the font middle. So the middle of the text is around here, which is basically the text size width divided by 2. Added from here plus the half the text, you will end up here. And that's it. Now you can just start drawing, and here the first circle is this eye. So I put an image there, position of the eye, the radius of the eye, which is this distance, then the color, as you can see, green, the thickness, and the line type. Also the same for the second eye, which is the second circle here. The only change is the position of the eye. Then I get an ellipse, which is this ellipse, the face, with the face center, which is this point, the face size, which is a rectangle, a width and height that represents this encompassing rectangle, the angle, which is this angle here, and this 0 and 360 represents if you want to have a full ellipse or if you want an arc. In this case we want a full ellipse, so that's why it goes from 0 to 360. Then the color, the thickness, and line type. Also we have a line here that connects the face center with the center of the text. As you can see here, the font middle and face center in blue, and thickness and line type as well. And we have a rectangle, which is this rectangle here, from P1 and to P2 in blue, and this -1 in thickness represents that you want it filled with that color, as you can see here. And finally, you just put the text with the same properties that you use to measure the text, and that's it. Now you know how to draw into images with OpenCV. In this video, I'm going to show you how to use blur in OpenCV. By using blur, you can get these results. You can have a face completely blurred, or you can have face or any other object smooth. So I'm going to show you the code for that. First, I create the 3 windows: source, medium blur, and Gaussian blur. I read an image and instantly show it as the source. This size is just an argument for the Gaussian blur. The larger the size, the more blurred the image will be. And here I set the region of interest, which is basically the object that you want to blur, in this case a face. So first what I do is to copy the image. I clone the image, and after that I set the region of interest in that image, so that way I get the specific headers for the object. You don't copy the contents here, you don't copy the specific pixels. You share the same data in this copied image and in object, but you're only working on the region of interest. That's the interesting part. So when you apply a Gaussian blur into the object, and to store it into the object as well, you're actually changing the data from this copied image. So after I do that, I need to copy the image again. So I clone it from the image, and then I do the same thing. I get the object from the copied image, and then I run the medium blur function to the object, and then show it with this line. That's it. So when you run it, you see that in this case we have, in the medium blur, you cannot really recognize the face because the blur is a lot. And in here, in this case, in the Gaussian blur, you can see that the image is smoother, but you can still recognize the face. So it really depends on your project which one you should use. But now you know all the alternatives and all the general alternatives. There are more blurring functionality in OpenCV, but these two represent nice 2 options for your projects. So that's it. Now you know how to blur an image to make it smooth or to make it so that you cannot recognize the object. In this video, I'm going to show you how to use the image morphology operations in OpenCV. First, I'm going to show you this image, and imagine that your task is to count the number of red balls and blue pens that you see here. For a human, that's really easy. You will say 3 red balls and 3 blue pencils as well. But the thing is, if for a computer, these 2 parts are different. So it will count 1, 2, 3, and 4. So what you want to do in this case, for example, is to close the gap here. So you want to merge these 2. Also, sometimes you will get noise like this in an image. So you want to get rid of that as well. And some other problems are that you have holes in some image, for example, here, and you want to cover or to close those holes. The other problem that you might have in this situation is to have two objects touching each other. So in this case, for the computer, these two objects will be just one. So image morphology helps you to overcome these problems. For example, here, running the OpenCV example in this image, I can erode or dilate the image, which are the two basic image morphology operations. If I move this to the right, it will erode the image. As you can see here, objects will get smaller and smaller. And if I go to the other way, I'm going to dilate the image, so the objects will be larger and larger. So now you can see the effect of this. We can start filling the holes, merging these two images, these two parts together. And also, if you move to the other way, you can start removing the unwanted noise, and also you can start separating this object. So that's the basic two functionalities of image morphology. But then if you combine them, you can get more functions. For example, the open functionality is first eroding the image and then dilating it. And the close functionality is first dilating the image and then eroding it. So if I move this to the left, I'm closing the image. So you can see that it closes the holes in the images in this part, and it merges these other parts. So the other way around, if you go to the other way, you will close the image. So as you can see, all the noise can be easily removed with this. And you can separate also this. So what I'm doing here is I'm using a structuring element. OpenCV uses 3 of them in this example, and the final shape of the objects that your image has will depend on the shape of your structural element. OpenCV uses, in this case, 3 structural elements that you can choose: a rectangle, a cross, and an ellipse, as you can see here. And depending on which one you use, the final image will look different. For example, if I go here, you can see with the spacebar you can change the structural element. So you can see that now I'm using the cross structural element. Here is the ellipse, and here's the rectangle. So we'll see the code, but first what OpenCV does is, for eroding, it combines this structural element with the image and gets the minimum between the structural element and the image. So for eroding, it will always get smaller and smaller. And for dilating, it gets the maximum. So it compares the maximum of the structural element and the image. So we always get bigger and bigger. Okay, so let's see the code. In here in the code, the important part is that you find an element shape here. And these numbers are just for knowing if you want to execute an open or close, depending if you're moving to the left or to the right. And here it's depending if you're eroding or dilating, if you're moving to the left or to the right. And the farther apart you are from the center, the larger the structuring element will be. And you can see here it's multiplied by 2 and plus 1 because it needs to be an odd number. So that ensures that for any number here, you will get an odd number. And that's it. That's the only thing that you need to know is there's these 2 functions. Dilate, you just put the source here and where you want to put it, and the structural element, which is a matrix with the shape and the size. And also erode, and the other 2 functions are this one, which is close, and this one, open. That's it. Now you know how to process your images, and you understand a little bit more of image morphology. In this video, I'm going to show you how to rotate and resize your images, as you can see here. So in the code, this first part represents the resize functionality. So it's just one call here. And if you just want to resize your images, this is the fastest way. So you can just call it with the image where you want to store the image and the size that you want the image. You have also two options here. You can explicitly say the size that you want the image, or you can specify here the to decimate, for example, 0.5 in horizontal and 0.6 in the vertical direction. So it will read either this or this to get the dimensions, and also the interpolation method. So the interpolation methods, these three are the best ones, and these other two, the linear nearest neighbor, are more simple, so they will get you more pixelized results. So unless you're looking for that, you should use these other ones. I prefer this one for scaling down my images to make them smaller. I prefer this one for scaling up my images, making them larger, and I use this one for general use. Also here you can see functionality for rotating and scaling at the same time an image. So you can put here the angle that you want to rotate your image. As you can see in here, it's rotated in 30 degrees in this direction, the positive direction, and it's scaled a little, so it's resized a little bit smaller than the original to make it fit here. And also it's rotated using the center as the reference, which is calculated here. You can get the rotation matrix with this function. You only need the point that you're going to use, the angle, and the scale that you want. And then you just call this function warp, and then you put the image where you want to store the image, the rotation matrix, and the size of the image. That's it. If you do that, you will get this image. If you want to rotate to the other side, you can just put here minus sign, and it's degrees. Okay, so now you know how to rotate and how to resize your images in OpenCV. In this video, I'm going to introduce you to the histograms, as you can see here. So when you have an image, you can represent that image using an histogram, which is a different view of this normal image as we're used to see it. So in here we have the pixels ranging from 0 to 255 in different locations, and in here we have a different view of that. So the x-axis represents the value of the pixels in general. So we have 0, the value 0 will be around here, and the value 255 will be around here, and everything in between. And the y-axis represents the number of pixels that have that specific value in the x-axis. So as you can see here, we have many different numbers ranging from different grayscales. So that's why we have this curve here. But if I start increasing the brightness of the image, you can see on the left that this image gets wider in general. And while it gets wider, you can see that the histogram is moving to the right. That means that all these pixels are increasing their value. So as I said to you earlier, around here are the wider pixels, and around here are the darker pixels. So it makes sense that if I increase the brightness of the image, the histogram will move to the right. And they start grouping in just this particular area because that's the maximum, in this case 255. So once you add more and more and more, you cannot add more than that, so they start grouping there. as you can see here. And the same happens when I go to the left. So you can see that it's almost white, so it represents almost all the pixels. Compared to this, almost all the pixels are 100% white. And if I start moving to the left, you see that all the pixels start moving in the histogram to the left. And also the image gets darker and darker. And the same happens here. They start getting at 0 and they cannot go less than 0. So that's why they start grouping there. So almost all the pixels now are at 0, and there are some others. In general, we can see that the image is very dark. So that's one thing. And then when you change the contrast, you can, for example, if you decrease the contrast, you're putting every single pixel very similar to the other. As you can see here, you lose contrast and every pixel looks similar to the other. And you can see that represented in the histogram as this. All the pixels start getting to the middle. In the extreme case, all the pixels look the same, 128, and that's represented with 100% in the 128 value here. But if you increase the contrast, all the pixels start separating from one another in value. So the extreme case there is to have just two values, white and black. So we have many pixels in the black part and many pixels in the white part. The part is the part that they can be. And if you go back, you can see how they start moving to the center again. So now you have a general understanding of how image can be represented with a histogram. And let's see the code for these. Basically, this is an algorithm for calculating the brightness and contrast. And then the image is just compared to these two values. So every pixel gets multiplied by this and then added by this. Then the image is shown. That shows the changes that I just did in putting more brightness, less brightness, more contrast or less contrast. And then the histogram is calculated here. It's just one image in one color, and the histogram size is here. This represents the number of bins, so you don't actually have, in this case, just one value for one pixel here. So as you can see, there are a group of values, and these are bins. So we have 64 of them, and all the values that are from here to here are considered as just one value. You can get more fine-tuned there, but that's enough in general. And the histogram is normalized, so you can look better at the data. And then the histogram image is all white, and then for each bin, they print a rectangle. These are the rectangles. So that's how it's calculated and drawn into the image. That's it. So now you know how to represent an image with an histogram, and you know what an histogram is. In this video, I'm going to show you how to use the k-means clustering algorithm in OpenCV. As you can see here, once you have many points in your program, you can divide them or cluster them into a known number of clusters, in this case 4. So what OpenCV is doing for you here is you give OpenCV a lot of points, which are basically data, in this case just two-dimensional data, x and y, position of a pixel, and then OpenCV labels them as one of the many clusters that you want. So you have to give OpenCV the number of clusters that you want and all the data points that you want. Okay, so you can use this to segment objects, for example, small objects from big ones using the width and height, for example, or any other property that you want to separate your objects. So let's see how this code is done. So first, this is one of the examples of OpenCV included, and it starts defining the maximum number of clusters as 5, and Basically, it uses a random generation of points. So if you can toggle them, and you will see many different runs. So in this case, for example, there's only 2 clusters, and in this case, you can see there are 5. So it goes from 2 to 5 in this case, as you can see here. So the cluster count goes from 2 to 5, which is maximum number of clusters, and this is not considered, so it's -1 here. The same here. So the sample count goes from just one pixel with just one sample up to 1,000 pixels. So after you have the samples and the cluster count, then it creates a matrix of points. Basically, one for each sample, you will need one row. So the matrix of points that you want to give OpenCV needs to have sample count number of rows and just one column. And in this case, we're going to use this type of points because they're just basically an X and Y, just two, as you can see here, there's 2 channels. It's a floating number because they calculate a random number. And then also you need a matrix for the labels. The labels are basically, for each pixel, for each data, you will know if it's from this cluster or this cluster or this cluster or this other 2. So that's the label. You still don't know where the label are, but you will need to give OpenCV a matrix for it to store it. So the cluster count in this line basically just ensures that there is at least the same number of points as clusters. So you don't want to have more clusters than samples. And also you'll need a matrix for the centers, which represent these centers of these clusters, as you can see here. The same thing, you will need one row for each cluster. So it's cluster count with just one column, the same type. And for this example, they generate the random sample data, but in general, you will have this data. So basically, points is a matrix where you will have all your data. And they basically, what they do here is just for each cluster, they get a center, a random center. So in this case, they just got these 5 centers. And then they just fill this point chunk is basically a header for this matrix. So this is changing this matrix. So it's filled with random values. It's a normal distribution with a 5%. So basically you have, this is the mean and the standard deviation is 5%. So that's why they're close to the center. Okay, but that's not the main point here because you will have that matrix of points. Okay, so you have that matrix of points, then you decide how many clusters you want to have, and then you give it this matrix, which basically you don't have any values. So k-means will calculate with these inputs, it will calculate this output. Also, it will calculate this matrix, which is basically the center of each cluster. And all of these are just specifics for the algorithm, so you can just keep it as with the same values. So what it does here is for each sample, it gets the label of it. So basically, after this function is run, you will have solved the problem. You will have, for each point, you will have the label. And for each point, you get the label that it was calculated for it. You get the point that you're standing at, and then you just draw a circle for it in the image at that point, at that size. You just draw it with that specific color. So depending on the label, you will draw it with a different color. So that's it. With this cluster ID, which is basically a label, it's basically already calculated in which cluster will end. So that's it. Now you know how to use the clustering algorithm, specifically k-means in OpenCV. In this video, I'm going to show you a watershed algorithm for segmenting images. The idea here is that you just roughly sketch the areas that you want to segment. Like here, the floor, roughly the left and right walls, and the rest. Also the ceiling. So when you run the algorithm, you get a nice segmentation of the areas that you roughly selected before. So this is the watershed algorithm using OpenCV. The idea here is that it uses representation of these images like a topographical image. And then the idea is they use the idea of having water coming out of these regions. And when the water from one region meets the water from another region, then it stops, and that is the boundary. So as you can see here, the boundaries are when this imaginary water comes out of these regions. So let's see the code for doing this. And this is the part for dealing with just the mouse. So what I'm just doing here is painting with white these regions to make it easy into the marker mask. Then here in the main program, what they do is they make different copies of the image. Marker mask, it's a gray scale image with just one channel, and then they convert that to an image gray, which is also a gray image, but with 3 channels, so that they can write these colors in it, mixed with the original image. So these are just for resetting the image, but this is the interesting part. When you hit W, the process starts, and this is what it does. Basically, we have the contours, which are basically the external part of the connected components. So for example, all these pixels have the same value. So they're connected for example, if you have a binary image here, all these will be 0 and all of these will be 1. So these are the connected components. And the contours is basically just what describes this shape. Also, the hierarchy here is it's the hierarchy of the image. For example, if you want to consider this as a contour and what happens with this contour in the center, which is inside the other contour. So all this hierarchy can be stored here. So then you call this find contours function, which just gets this image, a place to store the contours. A contour is basically a vector of points, as you can see here. So we will have a lot of them, so we will use a vector of points for describing the contours. Also, the hierarchy will be stored, and these are the options for the specific algorithm. This one here, for example, it says that treat the image with just 2 levels of hierarchy. Basically, everything that's outside and the holes of that. And this part here represents that if you have, for example, 5 points in a straight line, you just want the first and the last point. So you won't have the detailed vectors here, just the most important ones. So what the code does here is basically you have the markers, and you start markers with everything black. And then here you just draw the contours. So we already got the contours from this function. And basically what you do here is you draw the contours into this image. And as you can see, this is the key image. So everything in this image that is 0 will represent an unknown pixel. So we don't know what that pixel will be. But in everything that is a contour, we know that what it is. So we'll have a number like 1, 2, 3. So as you can see here, these pixels are, for example, this pixel will be 1, for example, all these pixels will be 2, these 3, 4, and 5. And the boundaries will be -1. So everything that is 0 is an unknown. And what you did here is just make some seeds. So here's the seed for example, 1, here's the seed for 2, 3, 4, 5, for example, and the rest is just 0. And then when you run the watershed algorithm, you will get an entire scene filled with the boundaries with -1. So as you can see here, you draw the contours with the specific number from 1 up to total number of regions that you have. And this -1 is just for field, for drawing the contours field. So then they just create a color tab. Basically, for each component, they want a random color. As you can see here, we just have 1, 2, 3, 4, 5 different colors randomly selected. And that's it. We're ready to call this function, which is really easy. You just call it with the first image, the original image, and the image of markers. As you remember, the markers image have the same width and height as this image. It has 0 in all the pixels that we don't know the value of it, and it has 1, 2, 3, or 4 in every seed part, as you can see here. So these will be, for example, this pixel will be 1, all these pixels will be 2, 3, 4, and 5. And after that, what this code does is just makes a representation of that for you to see. So it builds this image. And for building that image, it goes for all the markers, all the pixels of marker. It basically paints it with that specific color of the color tab. And finally, it just merges the colors of the watershed. As you can see here, just the colors. It merges it with the gray version of the image for you to see it here. So that's it. Now you know and understand a little bit more about the watershed algorithm and how to use it using OpenCV. In this video, I'm going to show you the grabcut algorithm in OpenCV. I'm running this sample of OpenCV, and by using it, you can just create a rectangle around the object that you want to segment, and then you can just press the N key on your keyboard. And after a couple of seconds, you will see that the image is segmented. You can also specify the background and foreground pixels. Holding Shift in this example and clicking on the image, you can specify which are the foreground pixels that you want to keep. For example, you can specify all these pixels being foreground, and you can also specify the background pixels while holding Control. So these pixels here, for example, are background, so you can specify that in the model. And also these small pixels here, they're just... So then when you press again the N keyword, you will see that they're gone. So by doing that, you can refine it and segment your object much better. So we'll see the code needed to run this, which is basically mostly this line. This is the most important line, which is the grabcut algorithm, which needs an image. It needs a mask. A mask is basically a matrix, the same size of the image, but it defines which are the pixels that are background, which are the pixels that are foreground, and which are probably background and probably foreground. Also, we need a rectangle like this, a normal rectangle, and these are temporary metrics that you don't have to set anything to them. You just pass it to the algorithm. This is just the number of times that you want the algorithm to run, and this is an option that you can say the algorithm to run with the mask. So specifically, you give the algorithm the specific mask that you want using the 4 constant values to specify the background and foreground, or you can use the rectangle. So you can say, okay, start with the rectangle, and OpenCV will start the mask with those values. For example, everything outside the rectangle will be background, and everything inside the rectangle will be probably foreground. That's pretty much everything that you need to know in order to use the grabcut algorithm. And most of the code is basically for dealing with click of the mouse and key presses and stuff like that. Here you can see the 4 constants that I was talking about earlier. Here's the background and foreground. And this is the probably for background and probably foreground. So if you set the pixels of the mask into those values, then you run the algorithm and then you will have the segmented image. And that's it. That's everything you need to know to run the grabcut algorithm. In this video, I'm going to show you how to match specific points from one image into another image. As you can see here, there are two different views of the same scene. The only difference of them is that they have been taken from different places of the scene. So this is how left eye will see the scene, and this is how a right eye, for example, will see the scene. So I'm going to run the example of OpenCV to match the points from one image to the other. So we can see that the first image is represented here in the left, and the second image is represented in the right. So you can see that first the important points are calculated and then on both images, and then they're matched from one image to the other. So as you can see, most of the points are correctly matching from one image to the other because there are horizontal lines. Any line that is basically not horizontal in this case will be an error. So the majority of the lines are correct. So we'll see now how we can match this in the code, which is very simple. The first thing that you need to do is you just open both images, then you need a detector. So in this case, we're going to use the surf feature detector, and you just initialize it. This number here is specific for each type of detector. OpenCV has different types of detectors, and the constructor has specific values that you need to read or understand the algorithm to change them. So you can just use the default ones. Then we're going to have two sets of points, of key points, one for each image, and you just need to call the detect function of the detector, giving as an argument the image and the key points to store. So that's the first part. You detect important parts, important pixels or key points of each image, and then you create an extractor, which is basically information about the key points for each image. So you have a matrix in this case, and you just call the compute functionality of the extractor. Same thing here, we have a corresponding descriptor extractor for surf, and you just need to give the algorithm the image, the key points, and it will store the descriptors here, which is basically information about the key points. So you do that for both images, and finally what you have to do is to match the key points from one image to the other. For that you need a matcher. So we create it, and we have a list of matches or a vector of matches. And basically you call the match function of the matcher. You give the descriptors of each image, and it will store the matches here. So after you do that, you can use the matches to whatever application that you're using. In this case, they just draw the matches, as you can see in this picture here. But you can access the points, the matches, to do anything that you want. For example, in this case, matching the points from one image to the other, you can use that to calculate the distance of the disparity from from this scene. Or you can use it to find an object in the scene, or many other uses. So that's it. Now you have an understanding of how OpenCV uses the descriptors and how to extract information about it and how to match the descriptors. When you're taking pictures, sometimes you can't fit the entire scene in just one photograph, as you can see here in this example. In those cases, you can use OpenCV to merge all these images into a single picture, showing the entire scene, as you can see here. This is usually called a panoramic image, or panorama. In this video, we're going to use a technique called image stitching to create the panorama. We're going to see the code required to create panorama here, which is basically the example provided by OpenCV. One thing here that you can see is that you have a vector of images. Those are the images that you have that you want to use for creating the panorama. Then you need to declare the panorama as a matrix. And this is the important part. You need to create an object, an stitcher object, with just the default values. And what you have to do with that object is to just call the stitch method with the list of images that you have, which is a vector of images, and also with the panorama, which is where you're going to store the panorama. And you have a status here. So basically, after you call that stitch method, you can test if the panorama is actually correctly created or if there's any problem. So if there isn't any problem, you have the panorama created, you can then just simply write the image to disk with this function, image write, with the result name, which is basically result.jpg, and the image that you want to write. That's everything that you need to do in the code. So now I'm going to run it. First, I'm going to erase this image here. And then I'm just going to go to where the example is already compiled, which is inside the build directory in the binaries. And the name is stitching. So the only thing that you need to provide to this example is the list of images that you have. In this case, I'm going to use these 1, 2, 3, and 4 pictures here. So I just give it to them. And what basically OpenCV is doing here is finding features or important areas of every image. And then it tries to match the features from one image to the others. By doing that, it uses that information to merge all the photograph into the final image. And as we can see here, it's almost done. And when it's finished, it should create the image. Here it is. So here's the resulting image, which is the final panorama. And here it is. As you can see, it is very easy to create your own panorama using OpenCV. In this video, I'm going to show you how to remove small parts of an image for restoring it. For example, in this case, I'm using the in-paint example from OpenCV. So you can see here that in this example, we have a couple of dots here and maybe some other areas that we don't want to have in our image. So the only thing that you have to do is just in this example, you only have to click on that and draw, just mark them with the mouse. And for example, we're also going to erase this little line here just to see the effect. So after you draw the circles or any shape that you want to remove from the image, you just press the space bar, and that's it. The algorithm is run. And as you can see, the points are gone and this little line as well. If you press R, you will see the original image. So you can see that here's a line, and you can't see the line here because it was erased. Also, these two dots from the original image now are gone. So let's see the code for this, which is here. The main part of the code is this one, in paint. In this function, you only need to give as an argument your image, your mask, which is a matrix where all the non-zero pixels there, all the non-zero values, have to be redrawn. So in this case, everything that you paint becomes a non-zero in this mask. And then here's where the output is going to be written, and this is the radio of the algorithm to search for pixels to fill the gap that was created because you want to remove that area from this using this mask. And basically this is the algorithm that we're going to use to paint those areas into here. And that's it. It's just one line, and you can enhance your photographs, removing dust or other problems that you may have. In this video, I'm going to show you how to enhance your low light images. Sometimes you have images like this one on the left because there isn't any light available in the room. In many cases, the best solution to this is just to get more light or get more exposure time or open the aperture of your camera more. But if you have a low light image and you need to get the most of it, you can process it and get something like this, which reveals more of the image. Okay, so how can we do that? Let's go to the code here. And basically what we do here is we have a vector of matrix, which is our image is split into different colors, R, G, and B, the 3 channels, right from the camera. And then we equalize the histogram for each one of these 3 color channels. So we equalize the 3 of them independently, and then we merge all the colors back into the processed image. That's why you see a slightly change of colors, which actually these are more similar to the ones from this scene. So that's it. Now you know how to increase the brightness of an image and also increasing the contrast by stretching all the possible values into the maximum, so you can get a clear view of what's happening in your low light image. In this video, we're going to see how to work with HDR images. HDR images, in this case memorial.exr, the included example, is an image with more than 8 bits per channel of color. So any display in general will have only 8 bits per channel. For example, your screen will have 8 bits. So the problem with that is that you have to choose between the dark areas or the bright areas, but you cannot see all of them at the same time. For example, in here, we're changing an HDR image of 16 bits into an 8 bits linear rescaling. That means that the darkest part of the HDR image are going to be 0, and the brightest parts of the image will be 255. So that means that you have to choose between looking at the bright parts or looking at the dark parts, as you can see here. Then if you somehow start to work and do a basic processing of the image, you can get something like this. If you start changing some parameters, and maybe you can see more of the scene like this. But if you use the sample of OpenCV, the Retina example, you can have an image like this, which is much more similar to the real scene that you were looking if you were taking the picture. So in this case, you can actually read the image with OpenCV, just running the example. In this case, I'm using this example, OpenEXR images, high dynamic range retina tone mapping, and then you can just add as an argument the image, the HDR image that you want to process. So then when you have your image ready, you can, for example, you can save the image to disk if you want to store a JPEG version of the high dynamic range image. So if you want to create an HDR, you can use this program, Qt PFS GUI, which is basically a graphical user interface to program PFS using Qt, the library Qt. So you can work with HDR images with this program as well. And you can, as you can see here, you can create new HDRs. And you can, for example, create an HDR taking the same scene with 2 different exposures. So you have, you load the images with that, and the wizard will help you here with the HDR creation. And you'll have, then you can load that image into OpenCV and get something like this. So basically the idea here is from different images of different exposures, you can create just a single HDR image, and then you can process that HDR image and you can have the full scene with lights and shadows in the same image, as you can see here with OpenCV. So that's it. Now you know how to load an image in OpenCV and how to display it in a normal screen with 8 bits by using a tone mapping function. In this video, I'm going to show you how to detect very simple shapes in an image. For example, let's say that you want to detect if an icon is inside a desktop. So this is one image and we want to detect if this specific icon is inside the scene. So I have two images, this one which is a normal desktop with the icon, and this other one which gives you a little more noise with the arrow on top of it. So let's see if we can detect our object, which is basically just this icon, in these two scenes. So let's run the example. It's chamfer example. First you give the scene and then the icon or the shape. And as you can see here, this icon is detected here. And basically the detection is a group of pixels. So the shape detected is a vector of points, as you can see here. Let's see if it can detect the icon in the other environment. And yep, it can detect it as well, as you can see here. So let's see the code for this, which is very simple. This is the example. The only difference from the example is just I uncommented these two lines because I wanted to use normal images. So for this algorithm to work, you need to have binary images. So basically, Canny converts a grayscale image into a binary image. So then you only need to call the chamfer matching function, and the results are, as you saw before, the results are vector of points. So the chamfer matching function will give you a vector of results. So that's why we have a vector of results. Each result will be a vector of points. And also it will return you the best shape that it has. So basically afterwards you only need to access to the results vector in specifically the best index, and you'll have the shape that best describes the icon or shape that you used. So as you can see here, for example, if the best is negative, it means that it doesn't have a match. So it means that there isn't any shape in the scene. But if there is a shape detected, it will be the index. So basically you can access it with results at the best position. And that's it. What it does here is for every point, it basically paints the point in green in the image. But you can do whatever you want. So basically, if you detect the image, you can return an example or anything that you want. As you can see, now you can detect any single shape, even with a small noise like this, for example, in your images. In this video, I'm going to show you how to detect objects in an image. For example, here you can see a detected face. The first thing that you want to do is to call the face-to-text example using the cascade argument. So you have to add this line here, cascade, and then you have to include the specific place where the cascade that you want to use is. And then finally, the image that you want to use to detect. So what is this specific cascade that I'm talking about? Is basically a file that represents an object. So OpenCV comes with many different already trained files that represent objects. For example, you can see here an eye, frontal face, full body or lower body, mouth, nose, etc. So all of these examples are inside user local share OpenCV hard cascades, or maybe some different directory that you have installed. But if you have followed the installation, the regular installation, you should have them here. So these are pre-trained files for detecting objects, and we can just use them. So right now I was using the frontal face default, this file, so it's used for detecting faces, frontal faces. So let's see it again, and we can see that it works very well. Also, we can use this example to detect nested cascades. That means we can use it to detect objects inside another object. So for example, let's run this with that option. And here you can have the option nest cascade, and it's the same thing. You just put here the path of the file that you want to use. So in this case, I'm using as a cascade frontal face, and then as a nest cascade, the eye. So I'm using this file as the main cascade and this file as the nest cascade. So I want to detect a face, and inside that face I want to detect eyes. So let's see how it looks. And as you could imagine, it detected both eyes inside the face. So let's see a little bit about the code of this. And most of the code of this example is for just dealing with the input of the image and the options. But the important part is here in the detect and draw function. So basically you need to give the function the image, your main cascade, and the nest cascade optionally. And also a scale optionally, which is basically if you have a large image, you can add, for example, a scale as 2, and the image will be half. Okay, so basically you have here a vector of rectangles, which are the faces, the detected faces that the output of the algorithm will be. And then you have, basically you have the original image, you convert it to grayscale. That grayscale, you resize it into the smaller image. If you use the scale option, it will be resized into a small image. And then they equalize the histogram. So basically you have a nice contrast and a good image to search for patterns. Okay, so then this is the important line. In the cascade, you call the detect multiscale, which is basically the algorithm for running detection. And you give the image, and you just pass the faces here. And in here, you will have the detected faces. Here you have some options. For example, here you can specify the minimum size of a face. So if you increase that, the speed will be faster because you have to search for a smaller number of windows, but you will miss small faces. So if you decrease that, you actually detect smaller faces, but you will have to look for many, many more windows. So it will be a lot slower. So then after the detection, for every face detected, they basically print it into the image. And then if you have a nest cascade inside that circle, inside that specific face detected, it detects, using the nest cascade, it detects the objects inside that specific object we already detected. And finally, it just draws the nested objects. And that's it. That's everything that you need to know to detect your own objects. So you can use different images and different cascades or nest cascades, and you can detect, for example, full body, lower body, left eye, the mouth, or the profile faces, or anything that you have here in the already trained examples, or even if you train something yourself. As long as you have one of these files, you can detect that object. In this video, I'm going to show you how to detect people in images. So I will take an image like this, and I will have OpenCV to run an algorithm, and it will detect people, standing people like this. So the code for doing that is basically getting the image. Then we have HOG descriptor, which is a feature descriptor of histogram-oriented gradients, and it's pretty good for detecting people in general. Also, we're going to use the SVM, or support vector machine detector, which is also very successful in detecting people. So we're going to get the default people detector for the SVM, and basically what you need to do now is just define a vector of rectangles. For each instance of a people detected, OpenCV will return you a rectangle. So we need a vector of rectangles. And here is the function for detecting the persons. So in the HOG, you just call detect multiscale, and you just give the image that you want to detect that you previously loaded. And in found, you will have the vector of rectangles. And then you have other options here, for example, the minimum size and the maximum size. If you decrease the minimum size here, you can detect smaller people that look smaller in the image. But if you decrease it too much, the number of windows that OpenCV has to search increases a lot. So it will slow down the process if you decrease this number. And also you can increase this number. This is okay because you can't have many large windows in an image. You always have more small windows. So it's not as bad as increasing this number as it is decreasing this number. And a number here is the number of neighbors detections. So sometimes you will have 2, 3, 4 rectangles, all of them indicating the same person, but you're only interested in just one detection. So if you change this number to 0, for example, you'll see all the detections, all the raw detections. But most of the time you want to group them together. So it's good to have a number like 2 in there. Basically, you now have the people detected in here in found, which is a vector of rectangles. So you can basically just use the detections. In this case, they're also filtering it because sometimes you can have the same rectangle, the same specific area detected because it's in multi-scale. So basically they first filter out the rectangles that are the same and they get the found filtered rectangles here. So once you have that, you can just do whatever you want with these rectangles. In this case, they just print them on the screen, as you saw in the example that I'm going to run here again. That's it. With you have these 2 rectangles, and now you can detect people in your images. In this video, I'm going to show you how to train your own classifier so you can detect your own objects, like a car, for example. The first thing that you have to do is to gather as many pictures you can from your object. So in this case, I'm going to use the image database for car detection from the University of Illinois. You can get it in this web page and download it here. And after you download and extract it, you can extract the positive and the negative images. The positive images are the images of the cars. So they have 550 images of cars for the training, and they have also 500 images for the background or negative images. So the negative images can be anything. The only thing that they cannot be is a car. So they can be anything, any picture. So in this case, all these images are 100 width and 40 in height. So you also need to describe for the positives the location of the image, of each one of the images, the number of objects that are in that image. In this case, all the images just contain one object, and then the location of the object. So in this case, the entire image, so from 0xy 00 up to the width and height is this object. If you have, for example, 2 objects, you can write the second location here or the third location here. Okay, that's the info that describes the objects in the positive part. Also, you need describing the negative part of the background, which is just a simple file which lists where the images are. And also, you need to create a VEC file, a VEC file. So OpenCV uses an utility that you can use is OpenCV create samples, and you can use it to see the images from a vector file, or you can use it to create a vector file. So let's use it to just to take a look at an included example of training phases. So if you run it with this argument, you just put the vector file here, and from the data files in the training phases, you put the width and height, you put that, and you can see the images used for training the phases in OpenCV. So let's create now this cars.vec. So we can use almost the same thing. So you need to do this. You need to call the utility OpenCV create samples. With this argument info, you have to give the cars.info, so the location of all the objects, also the number of objects that you have, in this case 550, and also the width and height of the training that you want to create. So in this case, because cars are larger in width than height, I just put 48 and 24. And also the vector is where you want it to be stored. So let's, for example, erase this. And if you run that, okay, it's done. It created 550 samples. We have cars.vec there. And we can, for example, look at it with the same command we did previously. So if you only run it, the OpenCV create samples with the vector and width and height, in this case is 48, and if you use the cars.vec, you can see actually the cars. So that's good to know that we have the correct files there. So now, the next part is to train the cascade. So we need to have the vector file and also these background files. So once you have those two, you can train the cascade with just this example here, the OpenCV train cascade. You need a directory to hold all the files. Make sure that it's without any files. Just erase everything in the folder. You give it as the argument here. So data is the folder that all the files will be created. Vec is the vector, the vec file that we're going to use, cars.vec we just created. The background is the background images that we're going to use to train the cascade. Here, the number of positive images and the number of negative images. Make sure that the number of positive images is less than the maximum number of the vector images. That's for some details in the algorithm, but let's just make sure that you have less than the total number of vector files here. Also, the number of stages. If you increase the number of stages, the trained cascade will be better, but it will be much slower to train. So in this case, just for this sample, I'm going to use 2 because it's quicker. But if you use a larger number here, like 20, for example, or 15, you will get much better results. Also width and height, and also the feature type LBP, which is local binary patterns. And this is actually faster than the hard cascade, which is very, very slow. So you can train a cascade with LVP in a couple of hours, and with hard cascade, that same cascade will be like you will need a couple of weeks. So LVP much faster. So okay, once you do that, the training starts, and you can check the parameters here. And what it's doing is basically training the cascade, and everything is being created here in the folder. So you can take a look. So once it finishes stage, it creates a file here. So you can actually interrupt the process and continue it because it goes from stage after stage. So once it's finished, it should create a cascade.xml. So it should be finished. Okay, that's right. And that's it. Now you can use this cascade to detect objects. For example, if we run our car detect, which is basically the same as the face detect algorithm, I just changed the painting part. So okay, if you use the cascade that we just created with this test image, you should detect the car. That's it. So the only thing I changed from the face detection algorithm or program is that now I'm printing a rectangle instead of a circle. So that's it. Now you can train your own detectors for detecting your own objects, like cars, for example. In this video, we're going to use a face recognition technique in OpenCV. to recognize a face between other faces. So the first step is to get the face recognition demo from OpenCV, and here's the code. And also you need to download a database, faces database, and just for an example, we're going to use the AT&T database of faces. You can go to this direction and you can download it here. And once you download it, you have to extract it, and you will have something similar to this. So you will have 40 subjects, and inside each folder you'll have 10 images of that subject. So we have 40 people and 10 pictures of each person in slightly different poses. So we have that database ready, and then you need to have a file that describes the images. For example, for each image, you have the path to the image, and then you have, separated by this symbol, you have an integer. This integer represents like the name of the person or the ID of the person. In this case, we're starting from 0 up to 39, so it's just this number -1. So we have all of them here, the corresponding number. This is the folder, and this is the entire path to get up to the file, and you get the ID here. Okay, so when you have those two, first you can compile it, and after that you can just run it with this as an argument, the CSV file. So the CSV file has to be talking about or expressing these images, and for all these images it will have a 0 on the type of the image. This one it will have 1, and so on. So what we're going to do is, by using this technique, we're going to predict a class. For this demo, we are trying to recognize the last subject, which is class 37. We can see that the predicted class correctly says 37, and we can see a confirmation of that in the actual class, which is 37 as expected. These two lines are the important part to look at. Over here we can see the feature face models for each class. Now let me show you the code for this. First, we need to read all the images and their labels. Then we have to define the test sample, which represents the image that we want to recognize. In this case, we're using the last one. They remove the last one from the list of images. So then the model is trained with just all the images up to the last one. So the last image is not considered in the model. In this case, the last image is actually this one. So we can see that image, for example. It's the subject 38 here and here. So this is the last image, and in this demo the last image is used as a test. All the rest are used as training. So this image is 37, so that's the answer where that should be, and that's it. So in the code we can see that the agent vectors are calculated here. This is the important part. They create a feature face recognizer. This is everything in the contribution module by Philip Wagner. Very nice code that it's given by him, and it's correctly predicted. Here you can have the prediction of the model. You have the model. After you train the model, you can predict if you give it a test sample. In this case, it's just an image. If you predict with that image, it will tell you that it's the face number 37, which is correct in this case because the actual class was that. Okay, so now you can change all these images into your own images and also change the CSV file. And now you can use OpenCV to recognize your own faces. In this video, I'm going to show you how to calibrate your camera so you can have a camera model and also a lens distortion model. The first step is to obtain a pattern. In this case, I'm going to use a pattern included in OpenCV, which is inside the doc folder, and it's called pattern.png. So I'm just going to copy it to a desktop, and you can see the pattern here. So make sure that you look at this and print it out. So in this case, we're using a pattern with 9 points here. So you only count the points that are inside. So it's in width, it has 9 points, and in height, it has 6 points. So you need to print this with very dark black colors. And if you don't get the black colors right, the program will not recognize the dots. So you need to print in a very dark color. Okay, once you have printed them, you need to take many pictures of that pattern in different locations. So for this video, I'm going to use the provided examples in OpenCV, example CPP, all the left camera. So in this case, we can see that we have around 13 images, exactly 13, with the pattern printed, and you can see that it's being viewed in different locations. So make sure that you print the pattern out and you put the pattern in different locations of the camera, these different views, close or far away from the camera, different angles. So make sure that you go to every part of the image, all the corners, for example. So once you have those images, more than 10, like 15 will be a good number, you can start the calibration process. So first you need to list all these images into just one file. And to do that, we just need to call this function here. So in the provided binaries of OpenCV, we have an image list creator. You need to call that, and then you just put the name of the file that you want to create. In this case, I'm using images.xml, and then you just list all the files that you have. In this case, I'm just putting left.jpg. So all the images with left will be included in that. So if you run that, you will have the images.xml created, which basically just represents, it's just a list of all these images. So once you have that, you can start the process of calibration. So the calibration, you just have to call the calibration side binaries of OpenCV with these parameters. Basically, the width is 9, as you saw here in the pattern, and the height is 6. So 9 and 6, because the inside points are in width 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 6 in height. And then you just need to put images.xml, which is a list of the images that you took after you printed this and took all these images. And when you run that, you can see that the algorithm is running, detecting the inside points of the pattern, and then it calibrates the camera. So after it runs the calibration algorithm, it gives you a reprojection error of, in this case, it's 0.39. If your error is more than 1, you should take more pictures or erase some wrong pictures that you have. You should always have an error less than 1 here. Okay, so once that's finished, you will have this file here, out camera data. And if you open that, you will see that you have all the information that you provided, but also that you have the camera model here, which is a matrix, and also the distortion coefficients here. Okay, so with that file, you can use it for your calibrated camera. So you can undistort your images or project something in the 3D space. In this video, I'm going to show you how to undistort your images. So if you have an original image like this, you can change it into something like this. Notice how the lines are straight in this image, and in the original, they were bent. Okay, so let's see how we do that. First, you will need to have your camera calibrated. That means that you will need to have this file, and see that file here. It basically contains two matrices, the camera matrix and the distortion coefficients, and that's what we need. So for the program, we need to call a function called undistort, and this undistort functionality needs the original image where you want to store the image and two matrices, this camera matrix and the distortion coefficients. So we need to get those two matrices from that file that you get from the calibration. So first you create a file storage reading that file, and then you can access to those nodes using the same name that it has here. So camera matrix in this part, you can access that matrix by going to that node in the file storage and just put that, you can put that information into your camera matrix here. Also the same thing for the distortion coefficients. Once you have those two matrices ready with the information, you just read the image from the command line, and that's it. You have everything for the undistort function. So you have the original image where you want the image to be written, and both matrices here, the camera matrix and the distortion coefficients. And that's it. After that, you can, for example, in this case, I'm writing the image to disk. And okay, so let's see if it runs. It's called undistort left01, and it should create an undistorted version of left01. So it created the image here. We have the left01 and the undistorted left01. So that's it. Now you can use OpenCV with your calibrated camera to undistort your images. In this video, I'm going to show you how to perform a perspective transform in an image so that you can change how you view an object with a perspective into a frontal parallel view. So for example, here you can see there a plane here is shown with a perspective, but if you select here the top left, top right, bottom left, and bottom right points of that plane, it will change the perspective into a frontal parallel view of that object, of that specific plane. So that you can, for example, see it closer, far away. And okay, so let's see how we can do this in the code. It's very easy. The only thing that you need to do is first, you need 4 points, 4 pair of points, which are the ones that I just selected here. So from the original image, those 4 points, they have to be in the same plane. And then you need to have 4 points in the projected image. So in this case, I'm just using, as you can see in the code, I'm just using a rectangle in the center of the image. So these 4 points here. And that's it. With those two arrays, you can call this function getPerspectiveTransform with the source and destiny points, and it will generate for you a warp matrix. Then you can use that warp matrix to transform this image into this image here. So you only need to call warp perspective with the original image, the image that you want to be written, the matrix that it was calculated for you, and just the size of, for example, the source image. And that's it. With that, you can call those functions and get frontal parallel view of a perspective view of a plane. So let's see another example here with another image here. So in this case, it's also rotated. So for example, here will be top left, here will be top right, bottom left, and bottom right. And you can see that it's correctly rotated. So the computer here is near the bottom part, so you can see it here as well, near the bottom part. Okay, so other things that you can do here, for example, is looking at this screen, you can do something similar. Top left, top right, bottom left, bottom right, and you should see from point of view of being parallel in front of the computer here. So that's it. With these functions, you can transform perspective views of planes into frontal parallel views using OpenCV. In this video, I'm going to show you how to calibrate and rectify your stereo images. So if you have a stereo camera, or maybe two cameras, very similar cameras, one next to the other, you may take pictures like this. But the problem is that first you have distortion in both cameras, and also it's hard to, if you have one feature here, it's hard to search for that feature into the other image because it could be in many places because of the distortion and because they're not really aligned, the images. So a way for solving that is to calibrate the images and rectify them. So by calibrating, we can eliminate the distortion or reduce the distortion, and by rectifying, we can find a feature in the left camera, in left image, we can find that feature in the right camera in just one line. So we see here that when the images are rectified, we can find, for example, a feature in the left image, for example, this point here. We can just search in this line and we will find that specific feature here. So as you can see here, if you're here, you just need to look to the left from that point to the left in this line, and you will find that feature from the left to the right. Okay, so this is very nice for working with stereo images because you can have information about depth and other features in very easy ways. Okay, so how do you get these rectified images? You need to calibrate and then rectify them, and you need to do that by first printing this pattern. Then after you print that, you need to put those two cameras, static cameras, you should move the cameras and take a shot holding this pattern, take a shot with both cameras. So take a shot with both cameras at the same time and repeat that process around 15 times. So you will end up with around 25, 30 images in total. Half of them will be from the left camera and half of them will be from the right camera. So after you have that, you have to create a list of images, and you can create the list of images using the built-in image list creator utility from OpenCV, and you just call it whatever you want and add all the images there. There's one problem, because if you do that, all the images will be like this, like without any specific order. But the problem is that we need to order them specifically. So we need to put the images in this order. Basically, first the left image and then the right image. So we have the first pair here, then we have the second pair, and so on. So it needs to be aligned in that way. First the left and then the right, then the second shot, and so on. So after you have that image list, the stereo calib.xml in this case, you can run the calibration. So the calibration is this also provided by OpenCV. It's one of the examples, stereo calib. You need to put here the W, which is the width of the pattern, 9, because it has 9 intersections here, and 6 as height, because it has 6 heights here in the intersections, and also the list of images. After you do that, the pairs will be compared and the features will be extracted, and it will calibrate the images, and then it will rectify the images. And the output of all of this program is two files. These two files, the extrinsics and the intrinsics parameters. And with those matrices that are inside those files, you can get this image and turn it into these rectified images. Okay, so that's pretty much everything that you need to know in order to get your images there using the included utilities in OpenCV and get these two files, which are the intrinsics and extrinsics parameters, which have all the matrices that you're interested in. For example, this is the camera model of camera 1, the distortion model of camera 1, the camera model of camera 2, and the distortion model of camera 2. Also in the extrinsics parameters are all the other matrices that you need. The rotation and translation matrix between one camera and the other, and all the other matrices that you need. So here in the code, you can see that you can undistort and rectify the images by using those matrices. So here in the code, you can see that here's the functionality, the stereo calibrate. You need the object points, the array of 3D points of the image, of the object, and also the points of each image, each camera. After that, you will get all these matrices, the camera and distortion coefficients of both cameras, the rotation and translation matrix, and with those matrices you can then call stereo rectify using those matrices, and it will give you the rest of the matrices that are missing. So with that, you will have those two files, and with those two files you can rectify your images. That's it. That's everything you need to know to calculate the rectification of your images. In this video, I'm going to show you how to generate a depth map. So you need to have a left and right image of the same scene already rectified, or if they are not rectified, you will need the extrinsics and intrinsics parameters that you can get from calibrating your stereo image. So basically, after you have your left and right image rectified, you can compute the difference in distance of the objects from the left or right image, and the larger the difference it is in distance from this part to this other part, it means that the object is closer to the camera. The same with your eyes. Any object that is close to you and you look at it with your left or right eye, it will see a large difference. But if the object is far away, then the distance between looking at it with your left or right eye will be almost the same. So we can see that the lamp here, for example, is closer to the camera, so that means that it's represented with lighter pixels. And for example, the books or the camera here are in the back, so that means that all those pixels are darker. Okay, so also we can use with this program included in OpenCV, as an example, we can choose between different algorithms. So for example, if we run the same example with other algorithm, we can see that we have different results. And we can see maybe another example here. And so changing the algorithm will change your disparity image. Also, if you have two images like these ones, which are not already rectified, but you have the extrinsic and intrinsic parameter, you can use this program as well. And you can call the program with the left and right image, and also with this argument for the intrinsic and this argument E for the extrinsic parameters. And if you run that, this example program will generate the disparity and also rectify the images. So the images are rectified and the disparity is created. Also, if you have that, you can add this argument P, and that allows you to generate the 3D world or the 3D points that are represented by this disparity. So all the points are stored here in just a simple file. So all the locations X, Y, and Z of the scene is there. So in the code for doing this is basically all the selection of all the specific algorithms and everything that you need to do for rectifying the images. And finally, at the end, you can access to the disparity image here. So also you can reproject the image to 3D, and you can access to the X, Y, and Z points here. So the important part here to access is the disparity that you can access here, and also the X, Y, and Z points that you can access here. So using that, you can access to your disparity image, which is a representation of the depth, and also to the X, Y, and Z position of your points.